This is AP Calculus Practice Exam 1. In Part 2, we will continue to work on multiple choice questions for which the calculator is not allowed. If you have not seen Part 1 yet, you can either click the link that appears in the upper right-hand corner, or you can find the link in the description. The graph of differentiable function f is shown above. If h of x is equal to the integral from 0 to x of f of t dt, which of the following is true? And then the choices are comparing the values of h at 6, h prime at 6, and h double prime at 6. So let's see what information we can figure out about each one of these values. H at 6 means we plug in 6 for x in the function h. So we simply plug in 6 for x right here, which gives us this. So h at 6 is the integral from 0 to 6 of f of t dt. So from 0 to 6, that's going to be from here to here. So this means the area between the x-axis and the curve from 0 to 6. So h at 6 is this blue area right here. We don't have enough information to calculate exactly what this blue area is. However, because we are reading from left to right, and this area is below the x-axis, we know this is a negative area. So one thing we know about h at 6 is that this value is less than 0. Next, we need to talk about h prime at 6. But how do we take the derivative of an integral defined function like this one? The second fundamental theorem of calculus tells us how to take the derivative of an integral defined function. There are two versions, the general case and the common case. For the general case, where you have a function for your upper or lower limit of integration, you plug in the top function and then multiply by the derivative of the top function, minus plug in the bottom function times the derivative of the bottom function. That's the general case. But if you're lucky, you get to use the common case. The common case is where the lower limit of integration is a constant, and the upper limit is just x. When this is the case, then the derivative will simply be f of x. Notice that h of x is the common case, so h prime will simply be f of x. Well, h prime at 6 will be f at 6. So this is the graph of function f. So what is f at 6? It is 0. So we know that f at 6, which is equal to h prime at 6, is equal to 0. Finally, we need some information about h double prime at 6. Looking at the previous statement, we have h prime at 6 is equal to f at 6. Taking the derivative of both sides, we get h double prime at 6 will equal f prime at 6. So this is the graph of f, so we should be able to get some information about f prime at 6. F prime at 6 means the slope of the graph at 6. So here is 6. So what can we tell about the slope of the curve at 6? Well, we know that it is positive. It's increasing. So f prime at 6 is definitely greater than 0. So why did I put an equal sign? I don't know. I should be saying h double prime at 6, which equals f prime at 6, is definitely greater than 0. As we compare all three, h at 6 is less than 0, h prime at 6 is equal to 0, and h double prime at 6 is greater than 0. That means these three are already in order from least to greatest. So let's look for the option that says that. And I think it's just going to be option A. H at 6 is less than h prime at 6, which is less than h double prime at 6. The answer is A. A particle moves along the x-axis with its position at time t given by x of t equals t minus a times t minus b, where a and b are constants and a does not equal b. For which of the following values of t is the particle at rest? Particle at rest means that the velocity is equal to 0. So our strategy will be, let's find an expression for the velocity and then set it equal to 0 and solve. We can find the velocity function by taking the derivative of the position function. This is written as a product, so let's use the product rule. So the first time through, we will take the derivative of the first factor and leave the second factor alone. But the derivative of this first factor is just 1. Maybe I'll just write it down to show that I did it. And we will leave the second factor alone, t minus b. And then we put a plus. Second time through, we leave the first factor alone, so t minus a, and we multiply by the derivative of the second factor. But again, that is just 1. This is an expression for the velocity. I'm going to simplify this a little bit by writing 2t minus a minus b. To find where the particle is at rest, we need to set the velocity equal to 0. Adding a and b to both sides of the equation, we have 2t is equal to a plus b. Dividing both sides by 2, we have t is equal to a plus b divided by 2. So the answer is b. The figure above shows the graph of f. If f of x is equal to the integral from 2 to x of g of t dt, which of the following could be the graph of y equals g of x? So let me get this straight. I need to somehow go from the integral to just plain g of x. This is reminding me of the common case of the second fundamental theorem of calculus, which says that when I have an integral defined function like this one, the derivative will just be g of x. So in other words, if I do f prime, that will equal g of x. And they are asking me which of the following could be a graph of g of x. But g of x equals f prime, and here is a graph of f right here. So really, I can just ask myself which of these could be a graph of f prime. So f prime is the slope of f at every point. But because this is linear, the slope is the same at every single point along this graph. In other words, the slope is constant. So the graph of f prime will be a constant graph, either like this or like this, some type of a horizontal line. But we also know that this is increasing. It's uphill. This is a positive slope. So f prime will be constant, but it will also be positive. So we're looking for something like this. So the answer is A. How convenient. Just for comparison, here's what the other options look like. The limit as h approaches 0 of this expression is which of these? If we try direct substitution and we put in 0 for h here and here, we end up with natural log of 4 minus natural log of 4. So the numerator is approaching 0. Of course, the denominator is also approaching 0. But if direct substitution yields infinity over infinity or 0 over 0, we can use L'Hopital's rule. L'Hopital's rule says we can take the derivative of the numerator and the derivative of the denominator without changing the limit. Notice that this is not the quotient rule. If I take the derivative term by term, I have 1 over 4 plus h. That's the derivative of natural log 4 plus h. Normally I would be talking about the chain rule and multiplying by the derivative of the inner function, but the derivative of 4 plus h is just 1. That's why I don't have to do anything with that. Of course, the derivative of a constant is 0. The derivative of h with respect to h is 1. This quickly simplifies down to the limit as h approaches 0 of 1 over 4 plus h. We can find this limit by direct substitution. Let's just put in 0 for h, and we get 1 over 4. So the answer is B. Remember, this only works if direct substitution yields 0 over 0 or infinity over infinity. The function f is defined by f of x equals x over x plus 2. What points x, y on the graph of f have the property that the line tangent to f at x, y has a slope of 1/2? Let me get this straight. The slope at the point x, y is equal to 1/2. We all know that when we talk about the slope of a curve at a point, we are talking about the derivative. So a shorter way of saying all of this is to say that f prime is equal to 1/2. So our strategy will be to find an expression for f prime and set it equal to 1/2 and solve. F of x is a quotient, so to find f prime, let's use the quotient rule. The quotient rule poem goes low d high, less high d low. Draw the line and down below, the bottom squared will go. So again, that's low d high. When I say low, I just mean write down the denominator. So x plus 2. D high means the derivative of the numerator. So that's going to be 1, which I didn't really need to write. So that's low d high less, subtraction, high d low. High means just write down the numerator. And d low means the derivative of the denominator, which is 1. So this is low d high less high d low. Draw the line, and down below, the bottom squared will go. Simplifying a little bit, we have x minus x. So those cancel each other out, leaving just a 2 in the numerator. But we want to know where f prime is equal to 1/2. So where does this equal 1/2? We can cross multiply a little bit. So that's going to leave us x plus 2 squared. Okay, I'm multiplying this diagonal, is equal to 4 as we multiply this diagonal. Taking the square root of both sides, we have x plus 2 is equal to plus or minus 2. Subtracting 2 from both sides, we have x is equal to negative 2 plus or minus 2. But this is really two different answers. This is negative 2 plus 2, which is 0, or negative 2 minus 2, which is negative 4. These are the x values. Let's find the y values that go with it. Remember, here is f of x right here. So f at 0 will be 0 over 0 plus 2, which is equal to 0. In other words, we have the point 0, 0. What about f at negative 4? That will be negative 4 divided by negative 4 plus 2. That's negative 4 over negative 2, which is positive 2. In other words, we have the point negative 4, 2. So these are the two solutions. So the answer is C. Let f of x equal 2x plus 1 to the third power, and let g be the inverse of function f. Given that f at 0 is equal to 1, what is the value of g prime at 1? Focus on the fact that g is the inverse function of f. So they are asking us to find the derivative of an inverse at a point. Finding the derivative of an inverse at a point is a three-step process. First, we find g at 1 instead of g prime at 1. Step 2 is to find f prime at the answer to step 1. And the final step is to go ahead and find g prime at 1. So step 1 is to find g at 1. How do we do that? we can use the definition of inverse functions, which says that if f and g are inverses, then if f at x is equal to y, then g at y is equal to x. Let's replace x and y with 0 and 1, which are given to us by this expression. Since f and g are inverses, then f at 0 will equal 1, if and only if g at 1 is equal to 0. But this is what we were trying to find for step 1, g at 1. And now we know that g at 1 is equal to 0. Step 2 is to find f prime at your answer to step 1. The answer to step 1 was 0, so we need to find f prime at 0. Well, we have an expression for f. We need an expression for f prime. So let's use the chain rule. So f prime of x will equal 3, and then this will be squared now. On the inside here we have 2x plus 1, but then the chain rule demands that we multiply by the derivative of the inner function. In other words, we multiply by 2. So f prime of x is equal to 6 times 2x plus 1 squared. We need f prime at 0. If we plug in 0, then this is just going to leave a 1. 1 squared is still 1. 1 times 6 is 6. So we just found that f prime at 0 is equal to 6. Step 3 is to find g prime at 1. But g prime at 1 will simply be the reciprocal of our answer from step 2. So g prime at 1 will be 1/6. So the answer is D. The line y equals 5 is a horizontal asymptote to the graph of which of the following functions? The key is that in your mind, you need to connect the concept of a horizontal asymptote with the limit as x approaches infinity. Specifically, you get a horizontal asymptote y equals 5 when the limit as x approaches infinity is equal to 5. So this question is really asking, for which of these functions is the limit as x approaches infinity equal to 5? Let's look at the first one. As x approaches infinity, the sine function will just continue to oscillate up and down forever between +1 and -1. Meanwhile, the denominator is getting bigger and bigger and bigger and bigger, so this overall limit is going to approach 0. So the limit as x approaches infinity is 0 for the first function. So that's out. For statement B, as x approaches infinity, this is just going to simply approach infinity. So that's out. For function C, as x approaches infinity, the denominator gets bigger and bigger and bigger, while the numerator remains a constant, so that value is approaching 0. For function D, what matters most is the 5x in the numerator and the negative x in the denominator. The 1 doesn't really matter. So the question is, what is the limit as x approaches infinity of 5x over negative x? Well, these x's will cancel each other out. So we get the limit as x approaches infinity of -5, and that's simply -5. Pretty close, but that's out. So the answer must be E, but again, let's look at what matters most in the numerator and the denominator. These are the only two terms which will matter. Only these terms matter because they are the fastest growing terms. The lower degree terms are left in the dust as x approaches infinity. So we are left with the limit as x approaches infinity of 20x squared over 4x squared. But obviously the x squared will cancel out. We are left with the limit as x approaches infinity of 20 over 4, which does equal 5. So the answer is E.